So this is 5.5. Counting, so we have to teach you how to count. So I like to call it the fundamental counting principle. It's kind of the basis of the whole section. And it basically says if there are this many ways to make one choice and this many ways to make a second choice, the number of ways you make both choices together is the product of those number of choices. Okay, so we'll say if there are m ways to make one choice and n ways to make a second choice, then there are m times n ways to make both choices together. So I think in the problem you have in those notes that he used was you got 3 shirts and 2 pairs of pants, right? So I got 3 shirts and 2 pairs of pants. How many ways can I make an outfit together? It's 3 times 2, 6. Okay, there's 6 ways. You can see it in if you make a tree, a decision tree, you pick the shirt, so it was, I think it was red, green, and blue, maybe. I don't remember. Red, green, and blue. And then for each shirt, you have khakis or jeans you can pick. So you see every shirt gets kind of multiplied into 2 outfits. See that? So for every shirt, it splits into 2 outfits. So that gives you, that's why it's 3 times 2, right? Because it multiplies. So every branch of the tree here is an outfit. So that's red shirt, khaki pants. This is green shirt, jeans, right? Each one of those is an outfit. So there's 6 of them. If you have to pick let's say a starting lineup for a baseball team, you have to pick the batting order. There are, let's say you got 9 players that are going to be your starters, you got to put them in a batting order. How many different ways can you put them in that batting order? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 things I have to multiply, right? It's the number of choices. I have 9 ways to choose the first batter in the batting order, right? And after I choose that player, how many choices are there for the second batter? 8. And then for the third, 7, 6, 5, 4, 3, 2. When you get to the end, there's only one person left, right? So there's only one way to make that choice. And we have a notation for that, right? It's factorial. So if you have, say, n factorial, you multiply n, and you multiply it by every whole number less than n as well, all the way to 1. Okay? So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I don't have my calculator. You can put that factorial in the calculator. So we put in 9, and then it's under the math menu, probability. Same place you go to the permutation and combinations, you get the exclamation point, which is what our factorial symbol is. 9 factorial is 362,880. So it turns out there are n factorial ways to rearrange n different things. We'll say n unique things. Go ahead.
So the non-factorial, that means that you have 362,000 different ways you can put that in order?
Yes. So remember when we were writing out sample spaces, and I said, you know, eventually there's so many you can't write them out. So it's going to be more important to just know how many there are. So if I want to know what's the probability that the other manager is going to pick this lineup, you know, it's 1 out of that, right? So that's, you know, if he's picking randomly, right? So we need to know how many ways things can happen and how many possibilities there are. We need to be able to count them. So that's why we have this section. We need to be able to count them without counting one by one, right? We need to get these counts with formulas. Okay. How many ways can you rearrange the letters in the word how about banker? So we're rearranging things, right? And how many letters are there? 6. Are they all different? Right, so it says in unique things, in different things, right? They have to all be unique. There's only one B, there's only one A, there's only one N. So it's just 6 factorial. You count how many letters and it's factorial because there's 6 ways to choose the first letter. And then I've already chosen that letter, so I have to subtract 1. And now there's 5 ways to pick the second one. And 4, and then 3, and after you've picked 5 letters, there's only 1 left, right? So you use the last letter for the last one. So it's 6 factorial. This is not making English words. This is just rearranging the letters. Okay. So 6 factorial. $720 ways. Yes.
What if you have letters that cannot be, or what if the word was like common?
Okay. I'm not going to write all this out. We'll just change the word. How about that? What about the? So if you have identical things, we have to make this adjustment. Okay, we have to take those away. So for instance, these two S's here, they're not 5s, they're S's. Okay. So if I switch the order of those two S's, I have it change the arrangement, right? Does that make sense? So I have to take out the number of ways I can rearrange the two S's. That was very dramatic. So we need to count things first. So how many total letters are there? 9? And then I need to count how many repetitions I have. So how many E's are there? 4. How many N's? How many S's? Is there any other repeaters? Okay. So you start out with the total number. If they were all different, it would be 9 factorial. Same as the batting lineup. Okay. So to cancel out multiplications, we have to divide. So we're going to divide to take out these arrangements. Okay. If these 4 E's were all different, how many ways could you rearrange them? 4 factorial, right? If there were, if there was a green E and a red E or whatever, and how many ways can you rearrange those 4 things? It's 4 factorial. It's 4 times 3 times 2 times 1. So we're going to divide by 4 factorial. That's going to take away all of the rearrangements of those E's. And how many ways can I rearrange the 2 N's? Just 2 times. 2 times 1, 2 factorial. These get multiplied here. And then 2 S's, 2 factorial. So you divide by the number of identical things factorial for every identical item. For every item that repeats, So non-factorial and here when I divide I have to use parentheses because I've got multiple things in here. What is 4 factorial? Without a calculator, what is it? 24, so I don't have to worry about the factorial symbols. What's 2 factorial? 2. I could have just said 4 there, right? So 3,780. So there were 362,000 ways if they're all different letters, but because we have so many repetitions, it drops it down to just 3,780. So it's a big difference, right? And you could do Mississippi and Alabama and all the states that have a lot of repetitions and other words and anything else. If you're talking about gender orders, if you've got 5 girls and 4 boys, how many different ways can those be born? Right? It's a lot, but there's a lot of repetition, so it cuts it down a lot. Okay. Well, what if you're not rearranging all of them? Let's say how many ways can I pick the first second and third batters out of 9. So I don't care about how many ways can I rewrite the entire batting order. I just want to know how many ways can I pick the first 3 batters, the first, second, and third batter. Okay, so I'm not picking all of them, right? So how many ways can I just pick the first, second, and third batters out of if I have 9 players? Okay. So one way is to say, well, for the first batter I have 9 choices. For the second batter I have 8. Right? For the third batter, I have 7, and I'm just going to stop. Right? I don't keep going all the way to the end. Does that make sense? So, right. I stop there because I'm not picking the rest. I'm just picking the first 3. So 9 times 8 times 7. 504. Okay. Well, how are we going to write this in a formula? That's the hard part. Okay. So how are we going to tell the formula to stop where we want it to stop? So why did we stop at 7? Because we're only picking 3, right? So if I were to write 9 factorial, what's the rest of this? If I kept going, what would be the rest? 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial, right? The rest of this is 6 factorial. Do you agree with that? It's 6 times 5 times 4 times 3 times 2 times 1. So in the formula, I'm going to take that 9 factorial, like I'm picking all of them, and I'm going to divide by 6 factorial, and that'll cancel those out like that. That's how we're going to make this formula work. Yes?
So when you type it in the calculator, would you type 9 factorial divided by 6, or would you do 987 then 6? Like, does it matter?
Well, I'll show you. Yeah, well, I'm not done. I got to hurry, I guess. So this is called a permutation. So it's NPR, that's the notation. N is how many things you have to choose from, and R is how many things you're choosing. And it's an ordering. These order matters on these. So it's N factorial divided by N minus R factorial. So in this case, this was 9P3. I have 9 batters. I'm picking the first 3. So 9 minus 3 is 6. So I divide 9 factorial by 6 factorial. And that cancels out the ones that I don't want. Okay? So in the calculator, he showed you this, right? So I can type in 9. I'm going to go back to that menu, that probability menu. So math, probability, and it's number 2, NPR. And then 3, it's 9P3. And we should get the same answer when we do. Exactly.